Hello everyone. In this lecture, we are going to convert the given regular expression into DFA, minimized DFA. So first we have to convert the regular expression into Epsilon NFA using Thomson's method. Then Epsilon NFA must be converted into DFA using subset method. Then we can reduce the number of states of the DFA. Okay. So first we have to construct Epsilon NFA for this regular expression. So here the regular expression is 0 bar 1 star 110 or 0 plus 1 star. Okay, union operator. So here first we have to give the preference for the parenthesis term expression. So here 0 plus 1 or 0 bar 1. Okay, 0 union 1 actually. So first we have to construct epsilon NFA for 0. So from one state to another state, we have to draw an arc, and that arc must be labeled by 0. Then we have to construct epsilon NFA for 1 below this diagram because we need to construct union operation. So here you have to construct epsilon NFA for 1. Then 0 bar 1, 0 vertical bar 1 means the union. So introduce a new state here and here. Then connect these two states by epsilon transition. Then connect these two states by epsilon transition. Then connect these two by epsilon. And connect these two by epsilon. Okay, this is the epsilon NFA for 0 plus 1, 0 bar 1. Okay. Then we need to perform star. Okay, so the precedence, the highest precedence is given for a closer operator, then concatenation, finally union. Okay, so next higher precedence is given for star, cleaning closer. So to construct star, first we have to draw the back arrow. Okay, reverse arrow from the final state of the regular final state of the epsilon NFA to start state. Final state of R to the start state of the R. R means any regular expression. So first connect these two by epsilon transition. Then introduce a new start state here and new final state here. And we need to introduce 4 epsilons actually. 1 epsilon we have already drawn. Another 3 epsilon, or connect these two states by epsilon transition and connect these two by epsilon and then connect these two by epsilon. Okay, this is a way for drawing epsilon NFA for star. Then this entire sub-expression is concatenated with 1. Concatenation means just we need to connect this with the another state, and it is labeled by 1. Similarly, another concatenation. So connect this with one more state and it is labeled by 1. Then finally 0. So connect this state with another state and it is 0. Now the start state of this epsilon NFA is this one. And this is our final state. So we can now number the states. So we can start numbering from 0. This is epsilon. So 0, 1. Then give numbers for the upper portion of the diagram. Then lower portion. Always number like this. Then joining node. So 6, 7, 8, 9, and then 10. So we have totally 11 states, 0 to 10. Okay. Now we need to convert this into DFA. Okay. So to convert the given regular expression into DFA, we can use the subset method. For that, first we have to construct epsilon closer for 0. Epsilon closer for 0. Okay. Actually, start state of DFA is epsilon closed, epsilon closer of starting state of epsilon NFA. Okay, starting state of DFA will be epsilon closer of 0 actually. So first we have to find epsilon closer of 0. How to find epsilon closer of 0? First we have to add this 0 as it is. Then from this state we need to check, is there any outgoing epsilon transitions? So from 0 there are 2 epsilon transitions outgoing. So 1 as well as 7. So we have to add both 1 and 7. Then from 1 we need to check, is there any outgoing epsilon transition? From 1 there are 2 outgoing transitions, 2 and 4. Then from 7, is there any outgoing epsilon transition? No. Then from 2, no outgoing epsilon. Then from 4, no epsilon. Okay. From 4, 1 is the outgoing edge. Okay. So this is our state A. Okay. We can give name for this state. Okay. This is our state A. Then we need to find transition on the state A. Okay. So we have to write from state A, transition on input symbol 0 and 1 here. Okay. So from state A, transition on 0 is, from state A means from these states we need to check. From 0 there is no outgoing 0. Okay. From 1 there is no 1. From 7, sorry, there is no 0. Okay. From 7 also there is no 0. From 2 we have a transition on state 3. Then from 4 also no 0. Okay. So we have only one transition on 0. Then we need to find transition on input 1. Transition on 1 equals from state A itself. Okay. So from 0, no 1. From 1, no 1. From 7, there is a 1. Transition on 1 going to state 8. Then from 2, no 1. From 4, 1 is going to 5. Okay. Then we have to find epsilon closer for this 3 and epsilon closer for 8 and 5. So epsilon closer for 3 means, first we have to start with 3. From 3, there is an epsilon going to 6. From 6, there are 2 epsilon transitions, 1 and 7. From 1, 2 epsilon transitions, 2 and 3. From 7, no outgoing epsilon. From 2, no outgoing. Then from, sorry, 2 and 4. Okay. 2 and 4. From 4, also no outgoing epsilon transition. So this is our epsilon closer of 3. So whenever we are finding epsilon closer for states, we have to give a new name for that. Okay. So this is our next state of a DFA B. Then we need to find epsilon closer for 5 and 8 or 8 and 5. Okay. So first we have to write both the states as it is. Then from 5, only one epsilon transition going to 6. Then from 8, no outgoing epsilon transition. From 6, there are 2 transitions, 1 and 7. From 1, 2 and 4. From 7, no outgoing epsilon transition. From 2, no. Then from 4 also, no outgoing epsilon transition. Okay, so this is state numbers, new state for the DFA. Now we have to construct this for all the states. Okay, construct like this. So now we need to consider from state B. From state B, transition on A. Sorry, transition on input symbol 0. So from B means we have to consider these set of states, and we need to check for a transition on 0. So from 3, no outgoing transition for 0. Then from 6, no 0. From 1, from 1 also no 0. From 7, no 0. From 2, 0 is there. It is going to 3. Then from 4, no 0. Then transition on 1. Transition on 1 from these states. So from 3, no 1. From 6, no 1. From 1, no 1. From 7, 1 is going to 8. Then from 2, no 1. From 4, 1 is going to 5. Okay, so now we need to find epsilon closer for these states. So epsilon closer of 3. Okay, so whenever you are finding epsilon closer for any state, we need to check whether we have found epsilon closer for the states already. Okay, we have found epsilon closer for 0 here, 3, 5, 8. So again, we need to find epsilon closer for 3. So just we can write the state B. Okay, then we need to find epsilon closer for 8, 5 or 5, 8. That also we have already found. The name of the state is C. Now from C, we need to find the transition on 0. Transition on 0 from C. Okay, C means these are the states. So from 5, no 0. From 8, no 0. From 6, no 0. From 1, 1 also no 0. From 7, no 0. From 2, 0 going to 3. And from 4, no 0. Okay, so this is transition on 0. Next, transition on 1 means from the same set of states, we need to check for one transition on 1. Okay, from 5, no 1. From 8, 1 is going to 9. Then from 6, no 1. From 1, no 1. From 7, 1 is going to 8. Then from 2, no 1. From 4, 1 is going to 5. Okay. So now we have to find epsilon closer for these states. So epsilon closer on 3 means epsilon closer of 3, we have already found B. Okay. So it is B. Now epsilon closer of 895 or 589. So it's a new state. So we have to find. Okay. So first write 589 as it is. Then from 5, epsilon going to 6. Then from 6, there are 2 outgoing epsilons to 1 and 7. From 5, actually, one epsilon going to 6. Okay. Then from 8, no outgoing epsilon transition. From 9, no outgoing epsilon transition. From 6, there are 2 outgoing epsilon transitions, 1 and 7. From 1, 2 and 4. From 7, no. From 2, no. And from 4, no epsilon transition. So this is state number D. So we have to continue like this. So now we need to find transition from state D. From state D, transition on 0. So transition on 0 from state D means from 5 there is no 0. From 8 no 0. From 9 0 going to 10. Okay. 10. Then from 6 no 0. From 1 no 0. From 7 no 0. From 2 0 going to 3. Then from 4 no 0. So this is transition on 0. Then transition on 1 from state D. Okay, from 5, no 1. From 8, 1 is going to 9. From 9, no 1. From 6, no 1. From 1, no 1. From 7, 1 is going to 8. From 2, no 1. From 4, 1 is going to 5. Okay, now we need to find epsilon closer for these two set. So 10, 3 or 3, 10 will be a new state actually. So we have to find it. Okay, 10, 3. From 10, no outgoing epsilon transition. From 3, epsilon going to 6. Then from 6, epsilon goes to 1 and 7. From 1, epsilon is going to 2 and 4. From 7, no epsilon. From 2 and 4 also, no epsilon. Okay, so this is a new state E. Then epsilon closer of 5, 8, 9. This we have already found. The name is D. So now from E, we need to find transitions. Transition on 0. From E, okay, transition on 0. So from 10, no 0. From 3, no 0. From 6, no 0. From 1, no 0. From 7, also no 0. From 2 and 4, 0 going to 3. From 2, 0 going to 3. Okay. Then transition on 1 means from 10, no 1. From 3, no 1. From 6, no 1. From 1, no 1. From 7, 1 is going to 8. Then from 2, no 1. From 4, 1 is going to 5. So now we need to find epsilon closer for 3. But epsilon closer for 3 is B. And epsilon closer for 5, 8, that is C. So now no new states are introduced. So we can draw the DFA diagram now. DFA transition table. So for DFA, we need to draw the transition table. So these are the states. Rows corresponding to states. columns corresponding to the input symbols. Here the input symbols are 0 and 1. So there are 2 columns. And the states are from A to E. Okay, A to E. So we have to write all the states here. Okay, then the start state is epsilon closure of starting state. Okay, epsilon closure of starting state of NFA is epsilon NFA is 0. So epsilon closure of 0. A means it's a start state. Then final state is the states containing final states of epsilon NFA, final state of epsilon NFA. Okay, so here 10 is the final state. This state doesn't contain 10. This state doesn't contain 10. Here also no 10. D also no 10. But E has 10. Okay, so E is a final state. So it should be marked as a star. It should be preceded by star. Then from A, we have to fill the table now. From A, 0 goes to, from A, we have got B and C. On input symbol 0, transition on input symbol 0 is going to 3, but we have to find epsilon closure of that state, right? So B is the transition on 0 for DFA. Okay. Similarly, 1 means C. So we have to mark all the states like that, B and C. So from B, transition on 1 and 0 and then finding epsilon closure means BC. So BC, then from C, BD, then from D, E and D, then from E, B and C. Okay, so this is our DFA. So now we need to minimize this DFA. Okay, so to find minimized DFA, we can first group the states. Okay, first write minimize DFA. Okay, by using partitioning method, we are going to find minimize DFA. So for that, first we have to group all the non-final states into one group and final state into another group. So non-final states are A, B, C, D and final state is E. Okay, initially we have the group like this and this group cannot be splitted into further. It means, suppose if we are considering A, B, C, D into one group, it means that at this point of time, all these states are equivalent. This is not equivalent, so it is in different group. Okay, so now this group cannot be splitted into further. So we need to consider A, B, C, D. So from A, B, C, D, 0. Okay, from ABC, from ABC, 0 goes to BBB. Okay, B is in this group. Okay, 0 goes to the same group. And 1 also going to CCD. Okay, we are checking ABC alone. From all ABC, 0 is going to B, the same state, same group, and 1 is going to CCD. Here also same group. But from D, 0 is going to E. Okay, this group, different group, and 1 is going to this group. Okay, it means from ABCD, for all ABCD, 1 is going to the same group. Okay, CCDD. But out of all ABCD, 0 goes to B, but from D, 0 goes to E. Okay, so it is a different group. So we have to now split ABC in one group and D separate group. D is in separate group, E is a separate group. This is the second step. Okay, now we need to these two groups are not cannot be splitted into further. So we have to check whether this group can be splitted further or not. So ABC. Okay, from ABC, on input symbol 0, all the ABC, from ABC, all are going to B only, this group. Okay, And from A, B, C, on 1, the A and B are going to this group C, but C is going to D, a separate next group. Okay, so C is not equivalent. So we have to split C from this group, and it is a new group now. Okay, now we have to check whether AB can be splitted further or not. Okay, so AB, from A and B, 0 is going to one group, the same group B, and 1 is going to the same group C. Okay, C may be a different group, but for both one it is going to C. Okay, so this group cannot be splitted into further. So now we can construct a new DFA, that is minimized DFA for that. Okay, so the minimized DFA is here also we have to write 0 and 1. And here from each group we have to take one representative. Okay, so from this group I'm going to take A, then C, D, E. So start state is A and final state is E only. Okay, and the thing is, instead of B, wherever B appears, we have to replace it by A. Okay, so here for A we need to write BC, no? So instead of BC we have to write AC. Then from C, okay, we have eliminated B completely. So from C, BD. Instead of BD we need to write AD. Then from D, ED. From E, BC. BC means we need to write AC. So this is the minimized DFA transition table. Next, we can construct transition diagram. So we have 4 states, A, C, D, E. A is a start state and E is a final state. Now we can construct transitions for this. From A, 0 goes to A and 1 goes to C. From C, 0 goes to A and 1 goes to D. From D, 0 goes to E and 1 goes to D itself. From E, 0 goes to A. From E, 0 goes to A and 1 goes to C. Okay, from E, 1 goes to C. So this is the minimized DFA for the given regular expression. Okay. Thank you.